Alô, testando, som, aí, beleza. Testando. Aí, tá bom. Testando, aí, ok. Good afternoon, everyone. Thank you, Luis. I'd like to thank the organizers for the opportunity to show a set of different kinds of results about graphene. Here, just 50th, a photo of our faculty in our 50th anniversary of our institute in Campinas. I'm somewhere here, but I confess that I'm working there since 2013. I still didn't met everyone of our faculty, but just a photo to show. So the group I participate there is Professor Douglas Galvão, who studied here. He's the leader of the group. GSOM means Group of Organic Solids and New Materials. In practice, we do whatever we do. Right now, we have one undergrad student, 2 graduate students, 1 postdoc, 2 arriving soon, and just let you know the faces of my collaborators from outside Brazil. Dr. Ray Balkman, experimentalist. He does a lot of applications of carbon nanotubes, and Dr. Susan Sinnott, with whom I collaborate in doing some classical molecular dynamics. So today I'm gonna speak about, I hope the time is enough to talk about 4 problems, 4 things we have worked recently regarding interesting results using graphene. One of them is related to cell-theory graphene. I'll give you details soon. Another one is about thermal expansion, not of graphene, but the holes in graphene nanomeshes. This is a recent, this temperature divider is something new that I'm doing in collaboration with Professor Luis. And the last topic is showing the potential to use graphene and other graphitic structures as solid refrigerant. I'll explain details during the talk. If we have time, I'll borrow Rodrigo's idea to show some subjects of things we do also, in case someone wants to talk about possible collaborations or ideas. So the first issue, the first topic about self-theory we published recently. It's a work I did with Douglas. It comes from one of Douglas' idea. He saw this paper published in Nature where the authors did the following: using an AFM tip on a graphene on top of a substrate. They made with the tip they made the hole, and they say they vibrate the tip in order to get the pieces of the cutted graphene folded on itself, like we see, for example, here. Then they left for days and some samples for weeks, 1 to 2 weeks, and they noticed that spontaneously this small piece of the folded graphene went away. Oops, sorry. this ribbon just grow, self-tear, and self-peel off the substrate and grow by itself along this direction. And they came out with a simple model where they hi, okay, they balance the energy due to adhesion of the top, the graphene folded on that these 2 layers of graphene. I'm sorry, I don't know if it's battery, but so they balance the energy, the gain of energy due to increase of the adhesion between these 2 layers of graphene, and the energy due to the adhesion of graphene and substrate, and they compute the graphene here, and also, most important, they consider the energy to break carbon-carbon bonds at the cracking edges, and they show that this model can qualitatively explain the effect. And some issues are the following. You need, okay, no problem. Right. Okay. Sorry for that. Okay, it's good now. So, some issues that the experiment couldn't answer are, for example, what's the onset of the crack growth propagation, the local atomic structure of the ribbon, the ribbons that's forming, the cracking edges, minimum size, because if you notice, the scale bar is on the micrometer scale. And some information about velocity, because they mentioned that after 1 or 2 weeks, the ribbon stopped growing, so it's not so fast. But at the beginning of the process, can we at least have an idea of the velocity of the process? So we defined a model, simple model like this, a piece of graphene with the hole, with 1 piece already folded on itself. We created two samples, 2 models with the 2 different chiralities at the edges, where the crack will happen. And then we just start the simulation, classical molecular dynamic simulations. We used a variable potential and the package, the LAMPS package, and we tried the width. Remembering the width is more or less the size. The idea is this surface area, the amount of this surface area, enough to produce the forces on the edges, able to break the bonds and then move forward. So we try with these sizes. I doubled the size, and nothing happened. But fortunately, when we tried widths about 80 nanometers, the system start the crack propagation. I have movies we did with one of the samples. Let me see. So this is the middle part of the system. We see the front end, let's say, in the middle part goes away, but interesting thing is to see this one of the edges. Okay. So we see that the front end make a kind of curve, but suddenly the tension that is concentrated at the edge is enough to start breaking spontaneously the the carbon-carbon bond, and the ribbon, ribbon growth continues. Here is a lateral view. Not pulling, just spontaneously, like in the experiment. They mentioned they didn't pull anything, they didn't apply any external force. In here, we also didn't apply any force, but for widths at with the size of 80 nanometers and above this, spontaneously we see the formation of this bond, of these breaking bonds at the edges, and the ribbon goes away. So here's some snapshots of the structure, one of the structures. We started from a structure like this. After energy minimization, we fixed the edges to avoid oscillations that could prevent this small size system to work, and then allow the system just evolve using algorithm to simulate a thermostat at 300K. In the first 1 nanosecond of simulation, we noticed that we estimated the velocity of this front from here to here, about this large value. In this first 1 nanosecond, we noticed just one carbon-carbon bond breaking here and here. One from this side, another from this side, not at the same time. It's not the breaking of the bonds are not simultaneous. You can start some breaks, some carbon-carbon can break here, after some time others here. But after 1 nanosecond, just 2 carbon-carbon bonds broke. And then if we keep this temperature, additionally for more 1 nanosecond, like 2 other carbon-carbon bonds break. We don't see much breaking, but if we increase the temperature, like we are showing here, if from this configuration we continue the simulation but increasing the temperature, then we see a lot of carbon-carbon breaks. So thermal fluctuations helps promoting the growth. But the large thermal fluctuations also caused the following. The pink atoms are the carbons that broke from the process, and the blue ones drawn here are carbons that reacted along the simulation. And when these carbons form the bond between the upper and bottom layers, the system gets stuck. And then, in this case, for this 1 additional nanosecond, the velocity decreases from 5 to 1. 1 is still large, but we are still in few nanometers moving. Remember, the experimental case, they go a little bit larger than 1 micrometer long, the ribbon. But the time is very low, very large. The average velocity is very low. And one of the possibilities we believe that causes the slow movement, slow rate of ribbon growth, might be the possible formation of carbon bonds, because they break at the edge, but some dangling bonds might, due to thermal fluctuations, to react with the bottom layer. Here, a set of structures with another system a little bit larger in the width. And again, for this case, double the width, even at 300K, we see that the structure, the front end goes away. It finished here because we have limitations on number of atoms to simulate, so we didn't simulate so large structures. But we can see that qualitatively the same thing happens. Here, just magnification of the shape of the edge along the crack edge, as we call it. When initially the chirality is zigzag, that's more or less the way the carbon bonds break. And when we have the armchair initial configuration, along the crack propagation, we see this very regular shape of the edges, the crack edges. So let me see. So that's the first of the result, the things we could infer from the molecular using molecular dynamic simulations for this particular problem of self-tearing and self-peeling off. We perform simulations with and without a substrate to verify that that competition between adhesion between the folded layer with itself and the detachment, the peel off of the bottom layer, and we verify that the process starts at with sizes about the nanometer scale. Another problem, okay, this is just, yeah, sure. No, it gets low. At the beginning, they go, oops, oh here, or maybe, oops. At the beginning, this is the structure the way we generated. At the beginning, they form this curve, so they move away, this part. I estimate the velocity of this middle point here, just subtracting the size and divided by 1 nanosecond. So it's a kind of a measure of the velocity. In the first nanosecond, let's say this front went to here. The second one, it didn't go as much as the first nanosecond. But we are in the nanosecond scale time. After that, it goes a little bit. So we increase the temperature to see the effect of the thermal fluctuations in the system. Okay, here we already increased the temperature and moved in comparison. Oops. In comparison to here, not much. So what we believe that after this initial stage, the velocity certainly drops a lot because one of the things might be this. If a dangling carbon by chance reacts with the surface below it, it will prevent it. We noticed in the several simulations we did that as long we saw in the trajectory of the simulations of the structures that when that happened, when one carbon reacts with the bottom layer, the front stops a little bit. So I think in a long time scale, sometime this bond breaks again and they continue. Right? Okay. Any other questions? Another thing I want to show, in spite of something that is not so new, it's a work I did with a student, a previous student. I work in the Fluminense Federal University from the end of 2009 to beginning of 2012. And there I had a master student, Newton, and we studied thermal expansion of graphene nanomeshes. Motivation, okay, I'll tell the motivation in a more or less fun way. Imagine that you're hungry, you like doce de leite in English. How can you say it? I don't know. Yeah, milk sweet, yeah. Dessert made of milk. And let's suppose you have a jar, it's tightly closed, and you don't know what to do. But then you physicist, or you remember the classic courses you did several years ago, you remember Holiday 2, I think, if you have a plate with a hole, if the material of the plate expands with temperature, the hole, we always ask the students, the hole will also expand or shrinks? People confuse, students think that the material grows in the direction to inside, but we know that the hole also increases, like the material not having the hole. So good for Garfield and everyone, because you can pour hot water in the metal lid of the jar. Metal lid has a larger thermal expansion coefficient. It will expand more than the glass, and then you can easily open. Okay, but what about at nanoscale? What about holes in a two-dimensional sheet, or the most thin kind of a membrane like graphene? So that's what we did. We knew that at that time some people has synthesized these graphene nanomeshes. Bottom is just a magnification of the top figure. So they can generate these graphene nanomeshes with several values of the hole diameter and neck size, the distance of the one hole to the other. So we defined our models, named the variables. L will be the hole size, N of neck, H of hole diameter. We consider periodic boundary conditions for the simulations. So, and then in graphene, we already know that the thermal expansion of graphene is negative, the planar, because imagine that the atoms can vibrate out of the plane. The carbon-carbon bond distance increases, the average size of the carbon-carbon bond increases with temperature, but the projection on the plane, because of flexural modes, decreases. And then there is a kind of apparent thermal contraction due to this effect. So we analyze the graphene nanomesh in the same way, and first we verify that the full length of the samples we studied, they decrease with temperature, okay, as expected. So it's okay. But what about the area, or let's say the diameter, the square of the diameter of the holes? We found that they increased. So differently from the behavior we expect based on Halliday 2. The structure shrinks, but the hole increases. So how to understand that? We estimated the linear coefficient of thermal expansion. And for example, for this structure, the black one is the coefficient for the whole structure. The dotted line is the linear coefficient of thermal expansion of the same structure without the hole, for comparison. So it gives practically the same amount of value of the coefficient. This one is this dotted line, dashed dotted line, is the coefficient of the neck. So the coefficient of thermal expansion of the neck is larger than the overall one. So the neck shrinks, let's say, a lot in comparison to the whole structure. And this dashed line is the whole coefficient of thermal expansion. So we imagine, okay, you increase the temperature, the hole increases, the neck decreases, the structure will disappear some time. No, it's not. This behavior will be until these values of temperature. After that, the thermal expansion changed the design. But then how to explain? Again, how to explain what's going on. So we analyzed the frames, the structure, and we noticed that at the edges of the hole, some atoms, at least visually, seems to move out of the plane more than the atoms far from the edges. So we we imagined a simple model. Again, we are taking into account the planar dimensions, like in the analysis of the thermal contraction of graphene, the projection on the plane. So imagine that these lines are like lateral views of the structure, and at a certain temperature, we have, in average, this size for the hole. Due to the vibrations of the edges, we have this, the projection on the plane provides this kind of size of the hole. If the temperature increases, we expect that the edges can vibrate more, larger amplitude comparison to the smaller temperature, and we expect that the size increases. So this is a model, and we did an additional test. I asked my student to take a set of frames of this from the simulations and just calculate an average on these pieces and along the time for several frames of the z coordinate of the atoms at the region 2 close to the edge and region 1 far from the edge. And we noticed that in average the circles are the average values of the out of plane coordinate of the structure of the atoms close to the edge, to the whole edges. And we see that in average they are 0.2 angstroms above the average size, average coordinate of the other carbon atoms far from the edges. So in fact, these atoms are really moving more than the atoms far away. So this ends this second stuff. The third thing I'm gonna mention is something we call temperature divider. We are doing with Professor Luis. Work is going on. And idea is the follow, or maybe the motivation is the following. We all know from classic electronics that this diode is one simple thing that allows the current, electric current goes from one sense and not from the other sense. And we all know from basic electronic that with a simple scheme like that, we can obtain the potential out in function of the input potential if you know the value of this resistance. So people for thermal phenomena for thermal transport, people has in research that has looked for this we call thermal rectified. One example we found in literature is doing this geometrical form for a piece, for example, of a graphene oxide paper. They show that it works as a thermal rectifier, so one example. So we have one equivalent thing for the diode, but at least we didn't find anything that could be related to this. And when we are studying the thermal conductance of a ribbon like this, with pieces of functionalized graphene and pieces of non-functionalized graphene, when we verified the equilibrium temperature profile, we got things like this. So here's temperature, here is the position along the structure. I put the structure here to make it clear. We notice these steps that are exactly on the positions of the pure graphene. Here we use the Miller-Platter method, where part of energy here is exchanged from this region to this, and then after the equilibration, we've got this pattern. We double the size, and again we observe these steps. We changed the method by applying a thermostat, two different thermostats at the end of the structures, and again we see the steps. And we are still doing more calculations to verify, and to see if you can, in fact, conclude that this kind of a structure can work similarly as a thermal divider, if included or if in contact of two different thermal reservoirs. So, okay, I finish the third thing. All right. Yes. Okay. In terms of temperature. Oh, I mean, this region will be after equilibrium at a temperature smaller than this side. This piece at a temperature smaller, like yeah, but not exactly as yes. That's the of if suppose, well, I don't have the numbers, but suppose you have a large heat capacity here. If we touch or you connect this part to another system, after some time, this other system will have this, supposing that they have a large heat capacity, or the size of this part is larger than the others. So it's something similar. We know that in the electricity, it depends on the impedance of the circuit we put in the V out, but something similar. At least we have not seen any study at least mention something similar. It's simple. It's not complex. I agree, but the simple that I think no one yet did. That's the point. Okay, the fourth thing I want to show you is a work we published recently. Thiago is an undergrad student, and the history of this is the following. Oh, I remember I also borrow from Rodrigo's. It's I did the calculation with carbon nanotube, but the references we read mentioned that the effect could be also observed with graphene and other two-dimensional materials. The idea is the following: how we come out with this work. I have seen this paper 2016 from some people from University of South Florida in India, and they studied using classical molecular dynamics. They use the same potential as we use. They investigate this effect. This effect is the following. I don't know if everyone played with a piece of natural rubber. If you stretch quickly or adiabatically a piece of natural rubber and touch like a sensible part of the body, let's say the lips, you stretch and touch the lips, you will feel a little bit warm, the natural rubber. In contrary, if the natural rubber is stretched and in equilibrium with the temperature of the place, the room, and you quickly release the tension and touch your lips with the natural rubber, you feel a little bit cool. This effect is called elastocaloric effect. Is a thermal response from the application of a strain in the material, tension or compression. And natural rubber it's well known, and some people, after studying the subject, I found that there is some research groups that are investigating the possibility to use materials like nickel titanium alloy, for example, as a solid refrigerant for cooling devices, cooling for several applications. And I saw this paper where the people here, using classical molecular dynamics, they simply verify the elastocaloric effect. They mentioned they found for 3% strain of tension or compression, by applying tension or compression strain on a carbon nanotubes, they found a temperature variation about 30 Kelvin. Then that student came to me asking to work on some project, and we reproduce this work and see later what we can do. Then I noticed when I was studying the literature, because I and those we are working in a similar project about the elastic effect in another kind of system. So we are studying the literature, and I noticed these guys forget the most important. Well, I might be wrong, but I took advantage of this in the following sense. They investigated the effect by just stretching the tube and releasing the stretch and compressing. Just like that. They first equilibrated the structure, they simulate structure at 300K, then they pull the structure and release the structure and compress the structure. Okay. They have not simulated one thermodynamical cycle. That would provide some information on efficiency, because I have found that people define for cooling machines this kind of efficiency for the case we want, the cooling case. It's defined as the amount of heat you remove from the cold place or the cold reservoir, thermal reservoir, divided by the energy you extract from your power, for example, to run the machine, to run the refrigerator. It can be larger than one. In this case, for this case, it could be larger than one. Usually, for our regular refrigerators in our homes, this number is about 3 to 4. The best ones could reach about, according to literature, 60% of the Carnot limit. That let's say it's about 6 to 8. What does this number mean? For example, a COP, coefficient of performance, of about 4. It means that it removes 4 times the energy it consumes from your power. More or less, that's the meaning of this coefficient. So our refrigerators are between 3 and the best ones 8. The nickel titanium alloy, people in their references, they estimate a value about between 4 and 5. There is one work that reported the value of 11, but mostly between 4 and 5. And let's see what we got. I think it was the easiest way to simulate one thermodynamic cycle. This is an adiabatic 1 to 2 and 3 to 4 adiabatic processes. 2 to 3 and 4 to 1 are constant volume exchange process where we allow the exchange of heat. And then doing the math, the calculations, we've got, here's just the temperature profiles for 2 nanotubes, different cases we studied. And we've got for 10% strain, well, we only studied the tensile strain and tensile release. We didn't analyze the compression because of buckling. Well, to avoid the situation of the tube gets this buckling deformation. So just tension and release the tension. And curiously, for the zigzag one, we've got almost more than 2 times larger the variation of temperature for 10%. Okay, it's a bit larger, but it's just for reference. But interesting is this. We've got values of coefficient of performance comparable to nickel titanium alloy. People is using a lot, is investigating a lot for solid refrigerant, to use as a solid refrigerant. The advantage of carbon nanotubes in comparison to nickel titanium is nickel titanium, the elastocaloric effect in nickel titanium relies on phase transformation under application of stress. In this case, nanotube didn't change phase, it just gets strain and release the strain. So imagine that you wanna run this thermodynamic cycle millions of times, and for the nickel titanium, it's an issue to how how to keep the material without defects after millions of times of cycles of changing in the phase, crystalline phase. So other papers in literature has estimated the elastic caloric effect for other materials, for boron nitride, for example. I found a paper, and but no one has done any calculation of or simulation of this coefficient of performance. So lucky for us, no one did. Then we published this. We were the first to publish this, and we hope people get interesting, because maybe you can include in a overall electronic system some solid refrigerant. I don't know, experimentally, I confess I don't know how to do this tensile strain, tensile release, but okay, so now I finished the fourth thing I want to show. Now just want to show some other things I've been done, just in case someone has an idea. In collaboration with Susan, we have been studying classically, by using classical molecular dynamics, interactions between graphene and metal. So this is, for example, is the first study on graphene-titanium interfaces using classical molecular dynamics. This is recently a paper accepted where we studied how graphene on top of an array of, in this case, C60 molecules, in terms of the distance of the C60s, how graphene deforms, if it will touch or not the substrate, in case it, like these pieces where graphene doesn't touch the substrate. So if these regions are or not thermally stable, if you increase temperature, for example, so we can, depending on the distances of these arrays, we can have like nano regions for reactions. So with another student, we have studied some elastic properties of, you might know this, might have seen these graphene structures. Also, we can simulate the graphene oxide using these potentials. We use it here and here. They have one interesting feature that it's classical, but it has some algorithm to estimate charge equilibration among the structure, based on some concept of in equilibrium, the chemical potential related to the charge should be constant at every site. Besides the dynamical integration for the positions of the atoms, they have an algorithm to do a kind of dynamics on the charges every set of time steps we want, to try to find out how the charges equilibrate among the structures, and the potential has some Coulomb interaction to be taken into account. So that's why we put this charge figure here, just to see more or less, okay, it's a classical approximation. Some of these should be checked using quantum mechanics calculations, but it's a way to try to bring to a large scale size this feature. So we can do that, and okay, let's summarize the results. Well, I might be overvaluing this, but in another set of problems or phenomena, we can say the graphene still surprising us. And in the first study, we just find minimal widths easing the nanoscale. Thermal fluctuation might help, but might help promote the growth of the ribbon, but also increasing the fluctuations, we can increase the chance of reaction between the layers because of the dangling bonds. In the case of the thermal expansion, we explain in the case of macroscopic plates that the hole follows the expansion of the material because we consider the material is homogeneous, is fully homogeneous. In our case, we notice that there is some non-uniformity on the fluctuations, on the thermal fluctuations of the material close to the edges, and because of that, we found that contrary trend for the thermal expansion of holes in graphene, and for the idea of thermal divider, functionalized graphene plays like the role of resistance, similar to the ohmic resistance. And at least based on these calculations, cylindrical graphene and graphene and other two-dimensional materials are predicted to be good refrigerants. Other collaborators, thank you all, thank you the sponsors, and thank you all for the attention. Yes, the experiment